Hello everybody, how's it going? Welcome back. Today in this video we're going to be talking about the task system finally, and the scheduler, and hopefully we'll get the syscalls. Um, but if not, that's cool too. I'm planning on this being a more short, more digestible video, kind of more to the point. We'll see if that actually ends up happening. So here we are. Let's just get right into it. Here we are in my module level, my mod.rs for my task module, um, and we've got a few different components to the task system in k4dos. So um, we have task groups in mod.rs itself. The task structure itself is defined. I'll get to that. We have a scheduler. We have signals we can do, like Unix style signals. Virtual memory for tasks, which is a very complicated topic that I will get into later. And then wait queues. So let's start with the top basically. So first of all, we have a global scheduler. Eventually, this will be a per CPU structure, per core structure. But since I'm only running on one core right now, that it's fine for me to just have a global static scheduler. So lazily initialized, and it's initialized in this function. And I'm gonna have a helper function to panic if it's not initialized. But um, I've never had any issues with that because I always initialize it like immediately whenever I have the heap set up. So then we have this wait queue, let's talk about the wait queues first, I guess. So a wait queue in k4dos is essentially something that anything that has a wait queue in it, like as part of its structure, is typically something that a process can wait on. So, let's say for example you have like for example this join wait queue. Say you have a process that forks itself, creates a subprocess, and then it wants to wait until that subprocess is done executing, like a forking exec kind of deal, like with a shell, right? Um, so uh, when that process is forked, and when it calls the wait for syscall, it actually, this is the wait queue that is used in order to push that process onto the queue. And then in the scheduler, it's also set as awaiting something, awaiting some signal, or awaiting some I/O, or awaiting a certain timer or something. It's just sleeping for any reason or whatsoever. So, sorry if you can hear the dog. Uh, um, what was I saying? With the join wait queue, yeah. So if a process wants to wait on a subprocess, or wants to wait on anything relating to its subprocesses, it uses the join wait queue, which is also global. I honestly probably could have it in the scheduler. I used to have a different structure for the scheduler, which let's go and look into that. But as you can see, it's very complicated. But essentially what we have going on here is we have our B tree map of tasks. That just allows us to easily look up any particular tasks shared pointer with by its task ID. It's just an efficient way to do that. We have a run queue. We have three basically essentially manual wait queues that I've implemented in here, but they all work together, so I couldn't use actual wait queue structures for them. But essentially what's going on here is we have a run queue, which these are tasks that are runnable, that are ready to be ran, that are ready to be switched to in a context switch, right? And it's a double-ended queue. So a task gets pushed onto the end of the queue, a task gets popped from the front of the queue, and they just line up ready to be executed, right? So and then we have the waiting queue, which the wait queue, the waiting queue, sorry, is used for the tasks that are basically in the wait queue, right, or in the join wait queue, that are either waiting for a child to exit or waiting some kind of I/O. Tasks in the deadline waiting queue are very similar concept, except these are ones that are specifically awaiting some kind of timer, or waiting with a deadline, right? So I need to keep track of these tasks separately because every time I perform a context switch, I need to check the timer and see if any of the tasks in this queue have expired their time, right? So it makes it easier to keep track of those, right, by having their own structure for them. So then I keep track of an idle thread. This is just a kernel idle thread. These are both, I should say, kernel tasks. So I'll get into the difference between a kernel task and a user task in a sec. But this is a kernel idle thread. It doesn't do anything when it's switched to. It just yields until there's another context switch that happens, right? Until there's another task that's ready to be switched to. And then I have the preempt task. And this is, by the way, a round robin preemptive scheduler. It's a proper term for that, I guess. What that means is the round robin part just means I'm using double-ended queue in order to cycle through the tasks that need to be executed in a round robin kind of fashion. And then the preemptive part means that I'm basically forcibly task switching every time there's a timer interrupt. So whatever task is currently executing when a timer interrupt fires, it is basically this context is saved in its context specific structure, and then the next context is loaded from the task that comes next, right? But that way everyone gets some processor time in a fair fashion, right? So preempt task, what that does is that's basically anytime we want to do a context switch, we first switch to the preempt task. This makes it a bit easier and cleaner to handle the previous task, cleaning up the previous task and all that, So it's like an in-between step, right? So basically how a context switch would actually happen between two actual processes is process A, is running, if timer interrupt fires, process A is saved, the preempt task is loaded and executed next. What the preempt task does is it just immediately in the loop calls a function that will do actual picking of the next task to run, right? So we'll get to that in a sec. And the current task is a pointer. It's just it's a smart pointer. It's a shared pointer to whatever task is currently being executed by the processor. So this is set by the scheduler right before it switches to the next task. And then exit task is another kind of, it's not necessarily a queue. It's more of just a list of tasks that have exited that are zombies essentially, and they are or they're dead and they need the resources cleaned up, which doesn't actually currently happen, by the way. But apologies about my dog. Anyway, and then I have the list of task groups, which I don't currently use the task groups or the process groups very much. Probably should, but it's a little broken right now, so I'm not going to worry about it right now. So when we create a new scheduler, a few things happen. First, we create our idle thread. Then we create the initial task, and this kind of needs to happen now. The net task, and then the PID equals 1 task, and this needs to happen now because of the way that the tasks, the PID task ID allocation is set up. The init task needs to happen so that it has PID 1, just for PostGIS compatibility and all that, Unix compatibility. That's just how it's typically done in Unix. So we create a new kernel task. Kernel tasks are given a function pointer directly to run that lives inside the kernel. So here it's startup init. This is actually a kernel task that just executes once and then execs into the actual init binary, which is busybox in this case. Opens all the standard I/O and all that, and sets it up to do an exec. So then we got our preempt task set up, and the preempt task, like I said, literally just calls switch in a loop, and switches up here, and it's like a bit more complicated than that, but we'll get to that in a sec. And then then we have got this Reaper task. And the Reaper task is essentially something that repeatedly calls a reap, which just gets the scheduler to clean up its dead tasks, which actually currently doesn't do much, because I realized that there's actually stray references, dangling references, or extra references to these reference counter pointers that are preventing them from being dropped. But either way, I'll figure that out eventually. When it starts becoming a problem, I'll figure it out, or when I'm bored. Either way. So in the scheduler, we can push tests onto the runnable queue, which will automatically remove them from the other queues. We can push them on the awaiting queue, which will again automatically remove them from the other queues. And we can push them. Wait, yeah, sorry, I was gonna talk about something that I've totally skimmed over it just now. So in the runnable queue, I actually implemented a slight amount priority system. It's just a little flag you can set on the push runnable function that essentially determines whether it's pushed to the front or the back of the queue. So if it's a given priority, that means it needs to run as fast as possible, and it's pushed to the front of the queue so it can be immediately switched to. If otherwise it's pushed to the back of the queue and has to wait its turn, right? So yeah, you can push awaiting. We can push deadline awaiting, which is just awaiting with a certain timeout to it. We said that we determined the deadline from the moment that's pushed into the deadline awaiting queue. So we get the uptime in milliseconds, and we add the duration. That's its deadline, essentially. We can check the deadlines by querying the time and seeing if the time has run out for any particular task. If so, we push it immediately onto a runnable queue with a priority queue, so that it can immediately execute whatever I/O is waiting on, or whatever, just to make it the priority. Just to make the deadlines as accurate as possible. And we can query the current task. We can find a task by a certain task ID or group ID or create a group. Exit the current task. This is kind of a special case because this is where a task stops executing, right? So we need to remove it from all the queues except for the dead queue, the exit task queue, and then we need to immediately test switch, or else we're going to be running into code that doesn't exist, right? So it's important to remember that for most of these functions that are being called, they're all being called in user space. Or at least with the user's code table active, right? So even though we can, these will only be called in ring 0 because they are kernel code, all the user stuff is still set up when we're calling these. Or the user processes stuff is still set up when we're calling these, like the page tables. And, these are all called from syscalls, right? So, or from an interrupt handler, either one. Either way, it's ring 0, but it's not entirely ready to completely run kernel code yet. So, in the exit current, we first check if init is exiting, in which case we immediately crash because that's not supposed to happen. Let's see here. And then if the process that's exiting was a child process to any parent process, and the parent process just let us know that it wanted to receive a sick child when its child exited, then we go ahead and let it know that its child exited. Otherwise, we go ahead and remove it from the parents' list of children. And the reason why we do that, this took me a while to figure out, is because typically when a process wants to know when its child exits, that means it wants to do the removing of its, that means that it needs to make sure the signal is handled first before it's removed from its list of children. Like if you look at where this is called from in the syscalls, so here we go. Where's the wait for syscall? Basically, if any process is waiting on its children to exit, like with the wait for syscall, then essentially how the wait queue will end up happening is if I remove the child from the parent process before the signal is delivered, then the signal will not actually ever reach the parent, because this wait queue, body, basically this wait queue condition check will check if there's any children, So anyway, I could work around that, but for now I'm just manually removing the child when the child exits. So anyway, a little tangent there, but where was I? So yeah, we close all its open files, and we move it from the run queue, move it from the waiting queue. Actually, we should move it from the waiting queue. I don't know why we're not doing that here, actually. Whoop. Self dot waiting queue. Self dot deadline, no waiting queue. There we go. Immediately fixed it. Let's just do t dot 0.pid. Okay, there we go. That should actually fix a bug in my code that I didn't realize was actually happening until I skimmed over the code. So thanks, YouTube, for being my auditor a little bit. So we can wake or resume, or basically just actually it should be true as well. we can what was I saying? We can wake tasks that are actually no, I'm not gonna break anything just yet. We can wake tasks that have already been waiting manually, and that can be done from a wait queue if its condition is met. You send signals to tasks. We can this particular function, try delivering signal, is different from send signal to, because the send signal to will just push this signal onto the basically the queue for pending signals for the task, whereas the try delivering signal will actually consume the signal if there is one and do the little trampoline into the signal handler. So, and I can go over that in a sec. Oh my god, this is already okay. And then I said it's going to be a brief video, and now I realize I'm 18 minutes in, but there's a lot to cover here. So might split this up into multiple parts as well, just because there's so much to cover with each part. So we can. This is basically used for stick return. Stick return is what happens when a process is done handling a signal. It's called from the signal handler. So it's a syscall. We wait for dead, and then we preempt. So, like I said, the preempt task, it just takes the current task, pushes it back onto the run queue. Or no, sorry, it doesn't push it back onto the run queue. It just switches into the preempt task from the current task. So, is that right? Well, I mean, I might have found another bug. I don't think. No, because that's right. Because it just doesn't. Right. Because that'll just be the preempt task. Okay, I realized something just now. what I realized was my preempt function that I used to jump into the preempt task never actually pops the current task off of the run queue. So when I'm and then when I go into preempt task, this switch function is only ever called from the preempt task. So when it picks the next task to run, and then it checks if there's a current task being run, of course there's a current task being run because it's a preempt task. So I'm going to make a little note to myself here to do fix the preempt thing talked about in the video. You're watching me debug my code live right here. So, yeah. Because the current task is going to be the preempt task. Wait, no, that's not right. Because, okay. Sorry, I got myself confused. The current task isn't actually switched from, the pointer to the current task is not actually switched from, it's not switched out in the preempt function. It's not until the switch function is called from the preempt task. So the current quote-unquote current task pointer is actually the task that ran before the preempt function was called. So this still works. Okay. So I'm going to delete that comment. Wow. I didn't realize that was what was happening until just now. There you go, folks. So, anyway. I want to get into how the architecture-specific stuff, the x86 stuff, works for the task switching. So I'm going to go ahead and jump into this. Basically, what this function does is it picks the next task and then context switches into it after saving the, let's just get into the context switch. So how the context switch happens, and the architecture-specific stuff for the context switch is this entire thing is unsafe by having an unsafe function because I'm never going to use it from the, switch function anyway. Hopefully. In x86, there are a couple different, remember those segmentation registers I talked about a couple of videos ago? Yeah, FS and GS are particularly special in that they are often used to offset, their base address is often used as an offset to access thread local and process local information. So FS base and GS base need to be saved and restored on every context switch. So that each task has its own local information, right? We switch out the TSS privilege stack table in case we need to enter a syscall during the next task, which we most likely will if it's a user mode task. And this privilege stack table is used for the syscalls. It's actually the kernel stack itself is not used during the syscall. You have to use a special stack pointer that is assigned to that task for its syscalls. Otherwise, we clobber other task stacks, or we could get a stack overflow, and it's just no fun. We xsave and xrestore for our floating point units, floating point unit information. That's a whole own thing that I won't get into right now. But basically, there's we gotta keep track of certain floating point scratch pad areas for floating point operations. They're kind of special. And then we switch to the next task address space, and then we actually do the context switch. And all the context switch does is, so you see it takes this context structure. So the context structure is literally just a stack of registers. And I call it stack of registers because all we do is we push the registers of we push the registers of the previous task onto the stack. We move that stack pointer into the old context structure, and then we switch the stack pointer to point to the new context, and then we immediately pop all of our registers off of that new stack. So And then we return to the next instruction, and that's usually the entry point or wherever the next task or it's switching to left off, right? So as far as like doing things like fork and exec, it's a very similar concept. When we exec into a new task or a new program, we have to set some certain registers. We have to make sure we end up in user mode, so we set the user DS, the user data segment, to all the appropriate registers, segment registers. We XOR to clear all of the rest of the registers that we don't need in order for it to do a context switch, because we don't want to leak information from the kernel or from a previous task into a new program, right? So we XOR everything with itself to set them all to 0. And then we sysret into the new exec task. So there's a whole bunch of complicated details that go into actually setting up new tasks. I could go into how we set up their stacks and how we set up their segment registers and all that. But I really do want to keep this video under 30 minutes, so I will get into that in the next video probably. There's so much more to go over with k4dos that I just haven't gotten to yet, because there's so much to talk about, and it takes me a while to talk about it. So I think next video will focus on the tasks themselves, or the next actual devlog. I might put out a little preview video, or like a YouTube short or something of me messing around with some of the programs that I've gotten running on k4dos. Spoiler alert, I've gotten Doom running on it, so yes, it runs Doom. And I've also gotten a ray tracer that I wrote a year ago, ported to it. So you can see the screenshots of all that on the GitHub page, and it's in the readme.md. Yeah, I'll get into all this probably next time. This is some real complicated, real geeky shit. So, but for now, thank you all for watching. If you have any questions or comments, as always, please leave them in the comment section, and I'll see you all next time. Peace out.